Welcome back, Witchlings. Today we're going to add a few more bricks to your palace of knowledge. We're going back to the citations from the talk on geologic time to aid us in understanding what other impacts we've had on Earth and its environment. One of the most devastating consequences of our knowledge about the atom explosively shook the Earth on July 16, 1945. Codename Trinity, the United States Army displayed the culmination of research into atomic theory as part of the Manhattan Project. It was the first ever test of a nuclear weapon. The device was nicknamed the Gadget, and it was an implosion-driven plutonium sphere equivalent to 20 kilotons of TNT. In an instant, it released enough energy to power 2,000 homes with the average consumption of a resident in the United States. The Trinity Experiment is what is known as an atmospheric test. It allows all radionuclides, dust, debris, etc. into the atmosphere without containment. I also highly recommend checking out this video. It's a timeline of all the nuclear tests that we've had during the Cold War. It's very fascinating. Roughly 1,400 of the 2,120 tests were atmospheric-based and allowed contamination to enter our atmosphere. As humans, we have a collective nuclear weapon yield of 540,749 kilotons of TNT. This would have been enough to power 60 million homes over the years. While not immediately observable, the Earth was coated in a fine mist of fallout. Radioisotopes were dispersed through rolling clouds of dust. The good news is that most of the radioisotopes resulting from fission are short-lived, but the bad news is that short half-life results in higher radioactivity. Most humans alive today have evidence of our rocky human history within them. These are generally in the form of long-lived radioisotopes or decay products within the bones and teeth. Decay products are more stable elements that a radioisotope decays into on its path down to stability. In addition, these long-lived radionuclides and decay products can be found in sediments across the globe. How do we know they don't just exist there naturally? Well, the age of the Earth is roughly 4.543 billion years old. Elements with a higher atomic number than uranium have a shorter half-life, and their instability means they are either extremely rare in the Earth's crust or non-existent. It was for this reason that plutonium-239 was singled out as a sign of the atomic age. It has a half-life of roughly 24,100 years, and therefore, plutonium made before 1945 would be unlikely to be in future scientific samples. It is for this reason that it acts as a forensic marker that shows our ability to impact this planet on a massive scale, just as we have in the past with agriculture and animal domestication. We've made a great many blunders in our quest to know more, do more, and achieve more. However, we've changed this Earth in ways that seldom any organism has. We've done this through using harsh chemicals that most other organisms would leave alone, and harnessing the destructive power of the atom. So it really shouldn't be a question of whether or not we've impacted the Earth. Rather, it should be a question of how, because we have many times in the past. As we discussed a little bit in our lead catastrophe talk, compounds and elements have a particular way of interacting with their environment at the atomic level. Greenhouse gases are no different than lead in that they have a particular way of interacting with their environment. Greenhouse gases are any gas that can absorb and re-emit infrared photons in the electromagnetic spectrum. This process occurs isotropically, meaning no preference is given to any particular direction. The absorption and emission has an equal probability to happen anywhere in any direction. These gases consist of water vapor, carbon dioxide, methane, nitrous oxide, and ozone, and they can be thought of as a spherical geometry for our purposes due to their isotropic property. These particles can be thought of as traps for photons within a fluid that would represent our air, because air is a fluid. Once these photon traps get into the environment, we can simplify where their hemispheres face. Half the hemisphere will always be pointing up towards space, and the other half will always be pointing down towards Earth. This would logically imply that in order for a photon trapped here on Earth to get out into space and escape with its energy, then it would have to travel through the photon traps, through the side-facing space, until it reached its destination. It should be understandable then that increasing the number of these photon traps in the atmosphere would result in a longer journey for the photon, since there's no preference to any direction. When one of these particles traps a photon, we call that the excited state of the atom. This means that it has increased energy and vibrates around. This increase in atomic vibration is what we know as heat. After some time, the atom releases another photon into the environment with much less energy, as some of the energy was imparted to other atoms during the collision. The more photon traps, greenhouse gases, that are put into the environment mean that more photons stay here on Earth because their journey is longer. This accumulation of infrared photons, causing atomic vibrations, gives us increased heat in our environment. Without any greenhouse gases at all, the Earth would be much colder than it is. That's it. That's how greenhouse gases work. It's simply a consequence of nature, and it happens no matter where they are. It's a well-observed phenomenon in both chemistry and physics. I appreciate you watching, Witchlings, and if you'd like to see more of my videos, please consider subscribing, and maybe even checking out my Patreon if you can. Until next time, stay safe and know that you are incredible. Bye!